For you as for me to leave Eric Mazur's lecture, of course, with the consolation that we can see it on tape. Several things were interesting for me. One is I knew David Hestenes in graduate school and had no idea that his article led to Eric Mazur's interest in education. And of course, we weren't able to stay for the punchline, the remedy. What's the right thing to be doing? So I'll watch the tape to find that out. Second thing I wanted to say, that there was one point there which I didn't agree with, and I don't know what you feel. He got to the top of the pyramid, the 1 in 260 of the starting students who went on to do a PhD, and he drew a star around them and said, I'm not worried about them. I worry about them, about that part too. I think, first of all, they're the ones who are the next generation who are carrying the torch. So there is something pretty important about them, even if numerically it's a small number. And I don't think, I used to think that maybe people became mathematicians or physicists, sort of, you couldn't stop them, right? I mean, they just were like born in that direction. They had a math gene or something, and you didn't have to take care of them. It would happen. But I don't believe that anymore. I think that, right now, where you almost feel a little bit the same. If we measure success by any standard measurements, then we should probably all be, working for Morgan Stanley or something. Now, I don't think any of us is going there tomorrow, but and that's a sort of a joke about the money part of the rewards, but the reward of, there are so many intangible but highly important rewards that if the system doesn't offer them, people make a different choice. So, and some of those rewards are internal. It is a great feeling to actually, to use your mind and understand something. But you need encouragement too. So I wouldn't assume that the special ones could be ignored. And I'm sure, he's obviously a fantastic teacher, so the special ones are learning like mad. Okay, now, what do I do with the Kalman filter? Wow. Maybe, again, try to establish what's the framework, what are the inputs, what are the outputs. So what will the formulas be formulas for? And then maybe a little discussion of those matrix formulas. But let me get the framework straight first. Okay. So, the point is, as in the list of topics, the point is that I'm going to end up with a very big system. Can I write it script A, script U equals script B or something? And that is a collection of equations coming at different times for a changing U and with measurements B. So let me look. This is discrete time, of course. I could be writing differential equations. Things are clearer in the discrete case. So so I have, say I measure some U0. Now that's a vector. So I start with some standard equation, A0, U0 equal B0. That's static. That's at time 0. I have a standard measurement equation. Fine. Okay. Now, time goes on. The system changes. But it changes by a known law. Now this is, of course, has got an error in it, E0. And that error, we're going to assume, has some covariance matrix, sigma 0. sigma 0, maybe I need to say sigma 0 E. Anyway, okay, fine. That we know how to deal with. Now the next step is time moves forward, so our next, this was a measurement equation. The next equation will be a state equation. This U0 is the state at time 0, and the state at time 1 is connected to the state at time 0 by some linear equation. Say U1 equal some F. I'm writing the, sorry, X, it better be U, and I'm going to change that letter F in a second as soon as I look up to see what's the letter. And so this describes the change of state, the dynamics between time 0 and time 1. But, of course, it's not perfect either. So there's an error, and let me use epsilon for the state error, and I'll use the index 1 where another person might use 0. That's obviously not critical. Okay, then we're in a state 1, and I take a measurement at state 1. So A1, U1 is some measurement B1 minus some error E1. Epsilons for the errors in the state equation, E's for the error in the, then, sure enough, U2 is FU1. Oh, and of course, and an epsilon 2. And then let's say we do a measurement at time 2. So I'll stop there. A2, U2 is B2 minus E2. Okay. And one further touch. Well, you see, I didn't insist on the same A matrix at every step, and of course I don't really have to insist on the same F matrix at every step. So this is the framework. This is the least squares problem. This is the big problem, AU equal B. I can, if I bring, you know, the U's onto the one side of the equation and the B's and the errors on the other side of the equation, then I have the big system that's to be solved. Let's do it. So what is script A? Let me just copy down that. What have I got in this matrix? And what's my unknown? U. Let's see if I can get it right. I ended up with 5 block equations. Everybody knows that, everybody's clear that these U's, typically the U's will be the same size, but probably we don't even have to require that. But they'll be vectors, not just scalars. And then the matrices will be appropriate size. Okay. And the A's appropriate to the B's. Okay. So if I just, all the stuff is, this is going to multiply U0, U1, U2. Let me put in the easy part first, and I had a B0 and then really a 0, assuming something like that is the B's. And then now comes my E, the error vector. This. Right. Maybe I'm using minus. Okay. And what's the matrix? That's, now we always focus on what's important. You see an A0 in the, we've got 5 rows, 5 block rows. A0, 0, 0 in the first, and in the third it's an A1, and in the fifth it's an A2, fine. And in the second it's U1, so maybe when I bring that over it will be minus U, shall I write it this way as F naught and minus I? Or maybe I wrote it as minus F naught and I. I've forgotten. It's not, of course, going to make a difference, but let me try to get it right. Okay. I'll see if I can capture quickly this A matrix. And again, to repeat that this, I was thinking this might get onto the web yesterday, but it will be there by tomorrow morning. Okay. Ooh, I don't know. Yeah. Okay. Well, yeah, I did use F in this chapter, so I'll stay with F. Okay. And now let me write this last equation. What do I have? I could make it this way, minus I F2, is that right? Or did I get F1, right? And 0. Okay. what's important about that block? Well, first, it's extremely large. It's going to get larger and larger. So I'm going to, essentially, I want to solve that system by least squares. And the most important outputs that I want are the most recent U, and it's P. There's a covariance matrix for the big problem, you know, big script P. And then there's the part of that big one that applies to the error in that, and that's the latest thing, so that's probably the most important to me. Okay. Now, what equation do I have to solve? I have to solve A transpose. I don't know how to write a curvy sigma. Just to emphasize, you know, this is like big A. This whole vector U hat, the best estimate, is this A transpose curvy, sort of fairly curvy sigma B. B, well, again, big B. That's the big system to solve. This is our fundamental matrix, and I don't think I maybe emphasized it in the previous lecture, but of course this thing is positive, definite, symmetric. It's got these properties we know to value, because sigma is positive, definite, symmetric. The covariance matrix is, its inverse is, and so we have an A transpose CA, all good. And what's more important, I can't say more, but equally important is, what's the shape of this thing? This matrix is block tridiagonal. This crucial matrix is block tridiagonal. Why is that? And then we could figure out what its entries are. It's A transpose. Now, you remember this is, yeah, let's see what it looks like. Suppose that was the identity for the moment, and the errors were white noise. You see that A transpose A would be block tridiagonal? Let's see. What's going to be the shape of A transpose A? What's the shape of this matrix? Block shape. 3 by 3, right? This is 5 by 3 block. 5 by 5 block diagonal. 3 by 5 block counts, those are. Okay, so the result is 3 by 3 block matrix, and is some 3 by 3 block matrix, and you know, well, we could figure out what it is. But this block tridiagonal aspect, this crucial part, is the fact that it's zeros there. Why are those zeros? You see that this row, this column, is perpendicular to this column, right? That's the point. We've built it in totally, that each column has some overlap with the next one. So there's a one diagonal away from the main diagonal. But then when we take that as a row into this as a column, to get this guy, it's 0. So this structure of connecting each one to only its neighbor is automatically, it's our constantly appearing framework that produces tridiagonal matrices. Here, block tridiagonal, because each of these is a system. Okay. Now, then the point is that block tridiagonal matrices elimination, as what we learned in that very first lecture was doing elimination on the thing, that it's a manageable process, right? I just have one step to do. I multiply that row by something to kill this, and then this row is ready to go. And I multiply the new row by something to kill this. There's a natural recursion. And then what about back substitution? Back substitution, remember, uses the upper triangular form, to go back up, the upper triangular form, how many diagonals in the up in the when I factor this thing into an LU, what's with them? This is the L, so it's certainly zeros there, but I didn't need to do any elimination here. It's a 0 here. So it's something, 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 something. And the U is the same in the opposite direction. It's just got a 0 there because that 0 there never leaves, and it's upper triangular. So there's the L and there's the block L and U. So the forward elimination is just one multiplier at every stage. The back substitution is just one substitution at every stage. And we can create formulas. So this is what the Kalman filter has to amount to. The Kalman filter has to amount to formulas for these steps forward. This is forward. This is prediction using L. Yeah, this is important point. Now I better say, what are the outputs? What are the inputs and what are the outputs? Per step. Per step. Okay. Input per step. Okay, what are the inputs? There is a new A K, shall I call it? There's a new F K. Well, let me put B first, because it kind of comes with the A. So there's the A's and the B's at the new step, and that's the measurement step, but then there's also the prediction step. You see, we've got two kinds of things here. We've got the measurement equations and the state equation, change of state equations, the prediction equation. So, so we could FK, say. And what are the outputs? Well, I think the best way, the right thing to do is to break each step into the two pieces. The two pieces. So maybe when I go to the new step, really the F comes before the A and the B at the new step. So I'm better off if I write F, systematically think of the F's as coming first, as giving the prediction of the new state based on the old one, our old estimate, and then we make some measurements at the new time, and that gives us an improved measurement. So like then A's and B's at the new time. Okay. So now what are the outputs? Okay. Well, the outputs will be what the outputs always are. The U's, the estimate, the new estimate, and the P, the covariance of that estimate, the error in that estimate. Okay. So, and we've got two stages here. So it looks to me like we're going to have four outputs. We're going to have an output at the end of this stage, this prediction stage. So this is like prediction, predict, correct. Oh, and then I'll have to tell you a little more. Because what I'm saying now is going to apply to the forward part here. Okay. The outputs from the prediction stage will be a new U hat at stage K, but it comes, at the prediction step, it hasn't used the B yet, right? So the frequent notation is with it makes a messy combination subscript. That's the prediction based on the old data up to K minus 1, not yet using K. Whereas an output after this one is going to be U hat KK. That's the best we know at the end of stage K. And that's like the thing we're after. And then we're also interested in the P, or whatever letter I'm using. That is what is the variance, the covariance matrix for the error in, everybody's remembering this, what P is the covariance matrix for the errors in U, K minus 1. And then we'll update that to P, K, K. Okay. And by the way, what should happen in this, in all our matrix formulas? Would you say PKK is, here's like an Eric Mazur question. Do you expect this to be bigger than this or smaller? Oh, you guys are too smart. Okay. Yes, this should be smaller. Why? Because we've got more information. So the variance should be smaller. Right. So our formula for this, so we're going to have two levels of formula. We're going to have the prediction formulas, and then we're going to have the correction formula. And actually, some of the formulas are not as bad, but then others are quite messy. So do you see like what's happening? At every stage, we're adding this row. Oh, yes, right. We're adding that row to them. So this is where we were at the end of stage 1. Now we can move on to the next time. So we add the prediction row. So it's like we're doing exactly, do all these calculations, but our matrix stops here if we're interested in this stage. And then it turned out better to separate it into two pieces rather than swallow the whole thing at once. And then now we've got to this point. We've got those answers. So we know those. And now we're ready to add a new row to the matrix. And that gives us a correction. Exactly the correction that we figured in recursive least squares. I mean, we don't lose what was done there. And that will take us from these answers to these answers. Right, right. Yeah. In fact, there'll probably be some formula like PKK is well, whatever the update one would have been here. So we've got 4 formulas to write down. Formulas for each of those, depending on the inputs and the previous ones. And there's this Kalman gain matrix, this K that we saw, that's built out of the other matrices. So it's not like something entirely new, but it's a convenient little bit of algebra to isolate that matrix as and have a formula for that. So we'll also have the Kalman, the gain matrix at that step. Right. Okay. Now when we finish introducing this row, we will have the best possible estimate based on the measurements and the state equations of the last guy, of U2. That's what we'll have, and that's usually what we want. Now, suppose we wanted the best estimate of U0 based on all this information that I've written down. What's with that? Suppose I proceed forward. This is all forward. Everything I've written on the board is forward. And that forward stuff takes me to U2 and the best estimate for U2. This is the winner. This is the best. Oh, where? Here. This is our best based on all best for the last UK based on all data. And this is its inverse. It's covariance matrix. It's covariance matrix. Okay. But let me finish that thought. What about U0? Do I have anything new to learn about U0 from what happened later? The answer is yes, absolutely. So that if I'm serious about U0, I should do back substitution. I said that I hadn't put anything on the board that went backwards in time. But the one thing I did put on the board that goes backwards in time is the back substitution triangular matrix. So what's that? What's the word for that? Do you know the word for what we get when we exactly smoothing? So there's a process of going backwards to smooth the earlier information if we want to do it. You know, if that information is important. And that then would be a further set of formulas. I'm not going to touch those, but I'm emphasizing that it's there. Right, right, okay. That smoothing is there. And actually, I have a problem to, maybe I'll mention this about smoothing. I'll even mention can I say this about smoothing, which is, and then I'll come back to the heart of the subject, which is here. So smoothing involves also, you know, going back up. And probably most people don't pay a lot of attention to it. Now, so I get things about problems in matrices, often from the sort of area of people who work in linear algebra. Well, a problem appeared that I'll state here, and I'll put it on into the lecture notes for this lecture. And let me right away offer a prize for a solution. Because when I saw that problem, who was put in by a friend of mine from Berkeley, and I don't know where he came up with it, but I realized it's got to be intimately connected to the Kalman filter. Okay, I thought, well, these guys, the readers of this journal, are like experts in linear algebra. They'll solve this problem 20 ways. But that didn't happen. The problem went month after month unsolved until the copy I have here of the problem said, would somebody please send an answer? And for me, that was so striking an example in real time, so to speak, of the cut, the separation between so much of linear algebra and what we're doing here. Of course, it's not totally separated. The people in numerical linear algebra know efficient ways to do this. And let me remark, while I'm making these general comments, that as always, we have a choice with this system. What's our choice here in how to solve that system? We have a choice of solving it by elimination or by QR, by orthogonalization. Do you remember that choice? And that choice in this world is called the square root filter, right? Here we've got a squared. So the formulas I'm writing down are the classical formulas that involve things about a times a. But for superstability and sometimes for speed, or sometimes you lose speed, those are the crucial issues. Probably you gain a little stability and lose a little speed if you change this, if you express A, I'm just going to put it up here and do nothing with it, A as Q, R. And of course you're going to compute Q and R recursively, right? New rows are added to A, so new things are computed here. So this would give the square root filter, which was like a bombshell in the Kalman world as an alternative. And I'm not at all able to report on the current state of that battle. Now, I was going to tell you this problem. So this is a problem then. Okay. So I have a tridiagonal matrix. A tridiagonal matrix. What can I call it here? T for tridiagonal. Okay. And it factors into lower times, yeah, say lower, the usual lower with ones on the diagonal, pivots, and upper. And what's the information about that we have about those? L has this has 3 diagonals. L has 2 diagonals. D has diagonal. U has diagonal above. And I'm not going to assume in this problem that the matrix is symmetric, positive, definite. Just tridiagonal is all. Okay. So that's sort of in doing elimination in the usual forward way I get to that. I'm going to put glasses on so that I can capture this fantastic problem right. Okay. So this is going in the forward direction, and I'll indicate those by pluses. The standard eliminating forward. Now, I don't know if you ever gave any thought to the possibility of doing the elimination starting at the bottom row and working upwards. Have you ever, there's no reason we couldn't do that. That order from 1 to n isn't the only possibility. What will happen if I do elimination upwards? Can we just pretend we have a matrix here? Okay. What do I do then? I take a multiple of that row, subtract from the row above to produce a 0 there. Then I've got something new. Then that from the row above. Now, what kind of a factor is that? What am I getting? So my original t was tridiagonal. Now I'm coming from the upward direction. And what am I reaching? I'm reaching an L. Instead of reaching a U, I'm reaching an L. The factorization in the opposite direction would be a U times a D times an L. And I just have to give that L is different from the other L. And that's like the reverse LDU. Okay. So that's coming up. Now here's the fantastic formula. We're interested in the inverse, the entries on the diagonal of the inverse. That's what all this stuff is going to be about. Okay, and here's a formula for it. That it's D plus, it's the diagonal entry of D plus and the diagonal entry of D minus the diagonal entry of T, all inverse. Well, I call that a neat formula. But I don't call the answers that I've seen to this question, which I don't have the answers with me. I don't call them neat. And I feel that if I were Kalman, I'd see, oh yeah, that's the formula. And of course, I believe that if this formula is true, which I think it is, that would generalize to blocks. Let me take at least like one special case of this formula. Suppose, let's look at what Kalman is most importantly looking at, the k equal n, the n by n block of the last block. So what do I get when k is n? So the point is, this is true for all the middle entries between 1 and n. But we can see quickly why it's true at n, and similarly quickly why it's true at 1. So I'm just hoping you might feel this is sort of interesting. All right, let me take k to be n. Then what is d minus nn? It's the diagonal entry. Let's see. At n, there wasn't any time to mess things up. This is row n. So what I'm saying is that that is the same as that. Here's my matrix T with n guy in the corner, and when I do elimination upwards, it's still there. It never got altered. All the alterations happened upwards. So if k is n, then this is just saying the T inverse, the n entry, is the same as the n entry inverted of D. And that, all I want to say is that special case is clear. That if I'm looking at k equal n, then that's the same as that. And it's just the regular last inverse. And that's what Kalman has to be computing. Because Kalman is in this part, before he does any smoothing, he's going for the n, the most recent one. And this is the quantity we want, and it's the block pivot. So Kalman has to do elimination on this matrix. Okay. So that's a comment with a question that I'll repeat in the notes. I guess you and I shouldn't feel bad if we don't find the answer, because a lot of other people didn't find it. But then it would be nice to do it, and nice to do it in an interesting way. So always the possibility that out of our work comes something that's of interest outside too. Okay, now what am I going to do with Kalman here? Should I write down some of those formulas? So we've got 5 things then: the new U after in the prediction, the updated, the corrected one, and the K matrix that enters the correction. Okay. I'm not sure which of these formulas to tackle. Yes, certainly. And this like, well, so this is like the state equation. This is the state equation. So I guess I keep thinking of this example that it might somehow reflect Newton's law or something. I mean, this guy is moving, and we're trying to find it. So it's where U is position and velocity or something. So U is a vector of position and velocity. And if we knew the position and velocity at the previous time, and say it's in free fall, then we could predict where it should be. But of course, it wouldn't be exactly correct. You know, our prediction would have made some assumptions, and those would be errors in epsilon 1. Right. Okay. Often, yeah. I suppose it would, if the time step was the same. But this allows, I mean, the strength and the weakness of Kalman is how general it is. I mean, well, you might say, well, it was a little bit limited to this single step. What if it was a second order equation? Would Kalman be dead? I mean, would his method fail? What do you think? If the state equation that controlled this was like Newton's law, second order equation, would we be dead? No. Because we would define U to be position and velocity. The old trick of reducing a second order equation to a coupled first order system. So we could get back to first order system. What we couldn't recover from is if the state 2 depended on the state 0, and if the state 100 also depended on 0. That would screw up the tridiagonal picture, and Kalman couldn't handle it. But apart from that, we have a very large generality here. And I was going to, having mentioned Wiener in the first lecture, this afternoon, I was going to say, okay, what did Wiener do? Because Wiener was at this job before Kalman. So what did Wiener do and what did Kalman do that was new? Well, what Wiener did was handle problems where the matrix was time invariant, where it started probably at minus infinity, so there was no trouble with the starting point, and the matrix didn't change. It was exactly like our matrices in that first lecture. You remember the comments we made when the very first time we looked at that matrix K and we said, okay, what are its obvious properties? Symmetric was obvious. Tridiagonal was obvious. And then the other obvious thing was that it was constant diagonals. Now, what's the point of that? The point of that is, as later lectures will focus on that special situation of constant diagonals, time invariance, the point is Fourier takes over. You can move into the frequency domain for those problems, and that's where Wiener lived. Right? I mean, he was a specialist in Fourier methods. Fourier analysis was like his bread and butter. So that he gave formulas in the Fourier domain, which are simpler, better, because you're using all that extra structure. But then Kalman showed up with his time domain approach, state space approach. So that was like a big revolution in this whole subject. That to move from Wiener's frequency domain approach, which was limited to time invariance and had a heck of a time as soon as anything was time varying, to Kalman, who could live with that. He could deal with time varying. He was really doing linear algebra for tridiagonal matrices. Okay, that's like the relation. So that when we're seeing at a later date how to deal with time invariant stuff by taking a Fourier transform, remember that that's where Wiener was working. Of course, it wasn't totally simple. I have to say this. Fourier requires time invariance, but it also requires, it likes no boundaries, like time invariant from forever to forever. And we don't have that. We've got, we're coming up to some time K. So these matrices are constant diagonals, but they end. They're singly infinite. Can I say it that way? This is my chance to mention the name, the two names, Wiener-Hopf. So Wiener-Hopf was about, and Toeplitz should be mentioned too, really. Wiener-Hopf is about matrices that start and go on forever, singly infinite, but not doubly infinite. Doubly infinite is the one where Fourier, we could call them Fourier matrices if we wanted, because Fourier just is perfect for those. Where singly infinite, Wiener and Hopf had to have a smart idea. This factors well into U times L. Here's. Do you want to know the Wiener-Hopf idea? The Wiener-Hopf, these are constant diagonals, right? The Wiener-Hopf idea was that I could factor it into upper times lower, not I, Wiener and Hopf. So upper times lower. And these will be constant diagonals. That's the thing. That's the thing. That multiplying that times that to give this will be no different from multiplying that second row times the second column to give the 2, 2, 2 entry. You see that? That there's at least you can hope that the Wiener-Hopf factorization preserves this constant diagonal, which is what everybody's living on in the Fourier domain, but it gives an upper times lower. Whereas when we took that matrix, so what if you try for the lower times upper? Actually, that's what we did. We did the factorization. Do you remember that factorization of the matrix K? Now I'm going to remove this devilish problem and this QR idea, square root filter idea, just to complete this thought, because I think maybe it's worth completing. I'm anticipating here Fourier stuff, but probably this is a good time to say it. What happened? Do you remember our factorization of two of our favorite matrix into L, D, and U? What did these numbers look like? What did the pivots look like? And what did these things look like? Do you remember there was what were the pivots for this thing? 2, 3/2, 4/3. Do you remember? The pivots were approaching 1. And what was the L? The L had 1s on the diagonal and had -1/2, -2/3, -3/4, so on below, right? And because it was symmetric, U was the transpose of that. So these are approaching what? -1. What I'm saying here is that the L times U, which is sort of the wrong order, it's not the perfect order, but it's approaching. It's converging to the perfect one. As I go down the list, I get -1, 1 in the limit in L, and in U I get -1. I get this is sort of what I'm converging to, of -1s and 1s and 1s and -1s. Those are this was the L and the U, but only in the limit. Whereas if I put them in the right order, in the other order, which is the right one for Wiener Hopf, they're correct from all the way along. Do you see that because actually we saw that factorization, I'll just write it in. 1, 1, 1, 1, 1, -1, -1, -1, -1, so on. 1, 1, 1, 1, 1, -1, -1, -1. Okay, so do that multiplication in the order U times L. What do you get? You get a 2, you get a -1, you get K. So I should have shown you that example from the start. That if, and I'm making it go forever. So that was the Wiener Hopf idea. And actually, now having got this far unintentionally on Wiener Hopf, where does Fourier come in? Why don't we see it? It never hurts to see an idea a month ahead of time, right? So where does Fourier come in? Well, Fourier would say, okay, what's the polynomial? Get into the frequency domain. So when I look at that or Wiener looks at it in the frequency domain, he'd say, okay, we have a -1 times an e to the -I omega, and a 2 for the constant term, and a -1 e to the +I omega. That would be the, whatever I want to call it, the frequency response function, the transfer function, the symbol, that's the right thing to look at for that kind of matrix. And what do I have here? Following the same rule, I have a 1 for the constant, and I have a -e to the I omega. And what do I have here? I have a 1 from the diagonal and a -e to the -I omega from the lower diagonal. And what do you suppose? A product of the so Wiener ended up factoring polynomials. That's the point. Is that you take the polynomial for k. That's in other words, you go into the frequency domain. In the frequency domain, you have some simple little polynomial instead of an infinite matrix. You factor that polynomial into a series, a positive power series going one way, and a power series in the inverse going the other way, and that tells you L and U. And of course, the whole thing depends on this constant diagonal. So Kalman couldn't, and Kalman would lose this plugging plotting through the state space time domain picture. But of course he gained enormously by having a much, much more general pattern. Is there a question or discussion? I hadn't intended to speak about this, but it's so highly, we're kind of in between, having seen in the very first lectures this K, and now seeing much more general stuff, but then seeing in the future a return to this constant diagonal. Well, probably Wiener-Hopf won't get mentioned again, but it's kind of fun to see it here as having mentioned this factorization UL in the reverse order in that crazy problem just popped into my mind. It's exactly the factorization that Wiener-Hopf did. So they, again, that's Wiener-Hopf. Wiener-Hopf deals with one boundary. The matrix comes up and it stops at 0. So Wiener-Hopf operates on a half line. Fourier operates on a whole line, no boundary at all. Or on a periodic one where it repeats and repeats and repeats, so the boundary's no trouble. Wiener-Hopf said, okay, we can still use Fourier ideas with an additional factorization if we go to a half line. Toeplitz took the problem of what do you do if it's an interval? Okay, then you've got two boundaries and additional complications. And then, of course, Kalman and everybody else, state space world, is dealing with something that's not time invariant at all. That's changing. These numbers are changing as you go down the diagonal. Right. Okay. You know, another little comment is, you know, the positive definiteness or positive semi-definiteness of this matrix is going to be reflected in the positiveness or the non-negativeness of this polynomial. So the Fourier world makes a beautiful, it's just the right way to deal with time invariant situations. Okay, I haven't done much here, have I? I've said what the outputs are, but not the formulas. I feel I want to give you the one formula that lies behind them all, and then these formulas, these Kalman formulas come from it. Yeah. I mean, some of the Kalman formulas you could guess. What's the best prediction I could make for U hat at the new time? Suppose at this point now I have the best knowledge I could of U1. Now I'm coming to U2. What's the best possible knowledge I can get of U2? So what's my U2 hat? Well, the best I could hope for, I mean, the only information I have is that it should be F1 times U1. So there's one, the simple one of Kalman's messy formulas. And then the covariance matrix for the error, and then let in the B's and so on. But the point is we're dealing with this, we're adding new rows and new columns to our matrix, and we have to know what happens to the inverse. So here's the formula that I'm going to emphasize. It's in any proof of Kalman, it's got to be there somewhere. And let me see if I can do it. I think I mentioned a special case of it before in connection with this matrix T, K, you remember? When we had K and then we let that go to a 1, which gave us the matrix T. And the question was, what's the change in the inverse? So this is the update of the inverse. Okay. So I'm going to have to peek here to get it right. And I'll identify where in this chapter 17 it sits. Oh, and then another thing that I hoped to do in this from this chapter was to take an example. You may well say, should have got going on that. I'm sure Eric Mazur would have got an example going. And it's this example of the steady model, which is just, I think, just fantastic, neat. But here, let me find the key formula for updates. Okay. So, derivation of the Kalman filter. Sorry, it'll just take me a second. Yep. Block matrix identities. Okay. So here, from the, I'll tell you the formula and then tell you how it's, well, you can see how it's arrived at. Okay. So we have a matrix. So we have a matrix T, and we want to change it. We want to change it by a matrix, and the most general kind of change I'm going to write in a way that will look a little strange. This is a correction to T, and the question is, what about the inverse? My formula is going to be that this is T inverse plus correction. And then the formula is going to be, what is that correction? Can I just, before I write that correction down, see how it applied to this case, to this problem? So suppose I started with T. Let me start with the 1. Start with the T, where this was a 1. And then I'm going to add 1 to the 1, 1 entry. How does that fit this pattern? If I wanted to add 1 to the 1, 1 entry of the matrix, I could do that with this. You see, this is supposed to be putting a 1 in the 1, 1 entry. So I'll let U be the vector. I'll let W be the number minus 1, just to get the sign right. And I'll let V be that vector. My old column times row. You see that this is then a square matrix with exactly this additional 1. So the question is, this then, the whole combination is my K, and you remember we studied K inverse, and took us quite a bit of work to find it, and this formula would be another way to do that. Now I'm ready for the correction, and then that's the lecture. Okay. For this correction, I do have to put on glasses, because it's a remarkable formula, which you can verify as being correct. But, so here it is. T inverse U W minus V T inverse U, that combination comes up, inverse V T inverse. How's that? So I offered a prize for any solution, a real serious prize for any solution to that little problem that I erased and will put on the web. I offer a smaller prize for not a proof of this, but I just claim that if you, what do I claim? I claim that if I multiply that whole mess by this matrix, T minus U W inverse V, multiply that by that whole thing, what do I claim to get? Identity. And it's quite satisfying, or frustrating, depending if you get it or not. But it's worth doing, worth trying, just to see this formula work. And the point is, these can be, that's a square matrix. This can be rectangular of whatever size it is, and this is rectangular. And the point is that, for example, that square matrix was 1 by 1. And here's the point. That, you see, this didn't save us from inverting a matrix. It exchanged the job of inverting this matrix to one we already had done, plus inverting this matrix. So it's exchanging one inverse problem for another inverse problem. Well, for two, you could say, because you have to know T inverse. But what's the point? What will be the size of this one in that example? 1 by 1. 1 by 1. That's the point. That's right. That's right. Exactly. But then it gave us an answer to an n by n inverse problem. What k was. Remember, this was our problem. K inverse. So if I copied that formula for this very special, let me call that special vector E or something, just for 1 and all zeros. Our special formula says that was our K inverse, is T inverse, and then T inverse U, U is E. Oh, I'm sorry. The whole thing, this would all simplify. I won't spoil it for you. This will simplify exactly because, as you say, 1 by 1s we can do. So that's the... Actually, what this does is to give you a choice. If you're doing Kalman, you've got one choice, which is to invert this matrix, and you've got another choice to invert this one. And I think one of those is called the Kalman filter, and the other one may be called the Bayes filter or something. And it depends on this. You see this U and W inverse and V, this is reflecting the new stuff as it appears in the A transpose sigma inverse A matrix. You're very kind to let me overrun my time. I won't overrun it further. So I'll see you next Thursday with probably some additional ideas about this topic, if you like. If you send an email saying you don't want to hear any more about that, it'd be okay. And then I promise to talk about finite difference methods and finite element methods a little bit. That's also on the program for next Thursday. Okay, have a good week. And no more storms, I hope. Thanks.